Greetings and welcome to another installment of quantile. This is 21 in our basic application series. This time around we're going to pick up right where we left off in part 1 of this mini-series with part 2. If you want to enjoy the blow-by-blow action, and I mean who would not, I suggest you watch this mini-series in full. You can find it playlisted under the quantile channel playlist tab. There you will as well find many other action-packed ready-made playlists. Okay, so let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Observing that this coin seems quite typical and knowing nothing else about this coin, we fashion a statistical test. We assume we are in possession of a fair coin, but we are prepared to challenge this belief if the result of 50 flips provides us with statistical evidence to the contrary. In a traditional decision theory style statistical test, we have two distinct steps. The first is to fashion a so-called critical region of our test statistic. Then after our experiment, we take our results and calculate our observed test statistic. In our little make-believe experiment, our sample proportion of heads was 30 and 50. Using this value, our calculated test statistic Z was about 1.41. This value is not in our critical region, and so as a consequence, we failed to reject the null hypothesis. So let's dig into some of the details here. Our world orbits our null sampling distribution. This is true not just for this example, but throughout statistical hypothesis testing. So this is our theoretical sampling distribution of proportion of heads when the number of flips or trials is 50, and the proportion of heads in our population is 1/2. This distribution, by the way, is very closely related to the so-called binomial distribution. This distribution here, the proportion of heads from a theoretical random sample of 50 flips, can be approximated or modeled, if we prefer, by a standard normal random variable. The probability that our standard normal random variable is between negative 2.3 and positive 2.3 is about 0.98, or 98%. Converting a normal quantile region, like the region between negative 2.3 and positive 2.3, into a probability, like 0.98, can be done in a number of different ways. You know, the old school way is to use a table. The more modern approach certainly is to use software. We can use an online calculator. I've included links in the video description if you want to check out some resources. Okay, so I decided our critical region for a normal approximation test statistic Z be a region of values less than negative 2.3 or greater than positive 2.3. If the null is true, values inside this critical region occur with a probability of about 0.02. And by the way, just to be technically correct, this is true here whether or not the inequalities here are strict. Said simply, if the null hypothesis is true, values in the critical region are fairly rare. But here's where things get, I think, really interesting. It turns out that if our alternative hypothesis is true, values of Z that are far away from the center, like those in our critical region, for example, could be much more likely than we assume under a true null hypothesis. And just thinking logically about this, not thinking mathematically, values that are far away from the center not only constitute evidence against the null hypothesis, but potentially offer evidence in favor of the alternative hypothesis. And this is exactly what the proverbial doctor here ordered to help inform our decision concerning our hypotheses. This is the key insight behind really all decision-based statistical tests. We start a priori with a significance level, commonly notated with the Greek letter alpha, first letter in the Greek alphabet. The significance level can be thought of as a probability we will erroneously reject the null hypothesis, or said another way, the chance of committing a type 1 error. For this example, I decided on a significance level of 0.02, or simply 1 in 50. We can choose other values as well for our significance level. Our critical region is the region of values under our null sampling distribution that occur with probability equal to our significance level and represent the values that most strongly argue against the truthfulness of our null hypothesis, but additionally potentially argue in favor of our alternative hypothesis. Okay, so how did we transform our sample statistic into our test statistic? Or said another way, how did we convert our sample proportion into our z-score? Well, here we go. If you're seeing this for the first time, it may look a little bit daunting, but to sketch things out, we have a function we're calling f. This function takes 3 inputs here. The observed sample proportion, the total sample size or number of trials, in our example, the total number of flips, 50, and also the population proportion value under the null hypothesis, 1/2 in our example. Our function hands us back or returns our z-score test statistic. And we're going to take a closer look at this function upcoming next in this mini-series. And by the way, for the sake of thoroughness, this function can operate on our sample proportion as a random variable, in which case our function will return a standard normal random variable. Make sure to check out part 3 of this mini-series, and that is it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.